What's going on, brothers and sisters? Welcome back. We are in the LANA Algorithm Example 2. We're working our way down through the steps one by one. In this video, we're going to focus on step 8, which is to state the grounded circuit equations. This is a revisit of step 5, in which we stated circuit equations, but we're going to use the information that we did in step 7 when we grounded the circuit to eliminate all reference to the ground node in each of our circuit equation types. To get started with step 8, let's recall the end results that we had from step 7. First thing that we did is we decreased the dimensions of our unknown node potentials by 1 because we claimed that we switched the ground node from unknown to node, setting it equal to 0. So specifically, we said the number of nodes in the circuit is 7. We subtract 1. Now we have n sub 0. When we ground the circuit, we set G equal to 0. That's the notation there. So now there are going to be 6 unknown variables in our node potential vector. The other thing that we did is we deleted the column of our full entire incidence matrix that corresponded to the ground node. In other words, we set G to 0 by multiplying on the right-hand side by our ground node deflation matrix, or our grounding matrix. That resulted in the grounded incidence matrix. We also deleted the corresponding entry of our vector U sub G by multiplying on the left-hand side by our grounding matrix and forming the grounded node potential vector U sub 0. Right multiplication deleted columns, left multiplication deleted rows. It's worth mentioning here that in this multiplication, we actually carried through the sub-block partitioning using the element type. So specifically, we had said earlier on in step 3 that the entire incidence matrix we could partition into element type. When we grounded it, we actually could bring the deflation matrix into each subblock. This is a good challenge for you watching at home. Go ahead and check the dimensions to make sure all of this works out. But what we say is that we have a grounded resistor subblock of our grounded incidence matrix. We have a grounded voltage source subblock and also a grounded current source subblock, which come from multiplying the appropriate subblocks of our entire incidence matrix by the grounding matrix from step 7. Now that we've refreshed our memory, let's go ahead and look at the step-by-step guide, and we'll start with step 8a, which is the cousin to step 5a. Specifically, we're going to state the grounded KVLs in node potential form. Remember that the node potential form of KVL said that the voltage drop across any element is the difference between the node potentials on either side of that element. The grounded form is literally the exact same thing, except everywhere we see the ground node in these equations, we're going to set that node equal to 0. It disappears from the KVLs. Remember in step 5a, we said that that node potential form of KVLs could be stated as the voltage drop across all elements in my circuit is the incidence matrix times the node potential vector. But we now can delete the column of our incidence matrix corresponding to ground. And then we can also delete the entry of our node potential vector, of our entire node potential vector corresponding to ground. When we do this multiplication and associate it as seen, we actually form the grounded KVLs, which is the voltage drop across every element is the grounded incidence matrix multiplied by the grounded node potential vector. And what that says is everywhere my ground node showed up in my original entire set of KVLs, set that node to 0 and delete it from the information that we're using to state those equations. We're going to call the matrix vector product A naught times U naught equal to V. That is the set of all KVL equations in node potential form for every single element in my circuit. There are going to be m different entries of V because there are m voltage drops. Of course, we noticed that the voltage drop vector was partitioned by element type. The grounded incidence matrix was partitioned by element type, and then the number of columns in each subblock of my grounded incidence matrix corresponded to the number of rows in my node potential vector with the ground node deleted. And thus I can actually bring in the U sub 0 to each subblock, and I see now I can state what I would call element-specific Kirchhoff voltage law in grounded form. So in particular, V sub R is A sub R naught times U naught, V sub V is A sub V naught times U naught, and then V sub I is A sub I naught times U naught. Each of these subblock equations is the exact identical version from the entire set, except that the ground node is deleted. It's set to 0. No new information is encoded in that scalar, so we just ignore it. For the specific circuit in this example, we can actually write the individual element KVLs, and the subblock partition is actually written right here. So V sub R is the first 8 elements of the voltage drops, because those are the first 8 resistors, the only 8 resistors, and that's A sub R naught times U naught, and then V sub V is A sub V naught times U naught, V sub I is A sub I naught times U naught, and that's exactly what we see. This is the scalar version of the more general matrix equation that we set up in this template form. Because we're going to refer back to the subblock equations, I want to really drill down and get specific. We said that the resistor KVLs in grounded form looked like V sub R is equal to A sub R naught times U naught. These are all the KVLs for the resistors where we've eliminated ground node. In scalar form, my grounded resistor KVLs would take the form that you see right here. Those are the actual values. Moving on to the voltage sources, we see that A sub V naught times U naught is V sub V, but this is a general linear systems problem because the left-hand side of this equation is known. When we look at the circuit diagram, the individual entries of that left-hand side vector are the defined values of my voltage sources in my schematic. That's a general linear systems problem. We can say something intelligent about that. For this example, the second subblock equation for the grounded voltage source KVLs looks like this by pulling off the appropriate entries of that larger matrix. The last one having to do with voltage drops across current sources is V sub I equals A sub I naught times U naught. The grounded current source KVLs take this form. With that, we finish with step 8a. Let's move on to step 8b, which is to combine the branch constitutive relations with the grounded KVLs. Remember that for the types of circuits we're studying in the linear algebraic nodal analysis algorithm, we only have one type of BCR that shows up in a meaningful way, which is Ohm's law. Specifically, we have this concept of Ohm's law in conductance form. Every time I see the vector I sub R, the currents running through the resistors, I could write that as a diagonal matrix, the conductance matrix, which is the diagonal elements defined by 1 over the resistive elements for each corresponding resistor, multiplied by the voltage drops across the resistors. So I could write I sub R is equal to G times V sub R. But from step 8a, every time we saw V sub R, we could replace that as A sub R naught times U naught. The voltage drops across the resistors are the grounded incidence matrix times the grounded node potential vector, which means in my BCRs, in my Ohm's law and conductance form, when I say I sub R is equal to G times V sub R, I can use this equation to replace V sub R in terms of the node potentials. So now I have the currents running through the resistors are the conductance matrix multiplied by the resistor subblock of the grounded incidence matrix multiplied by the grounded node potential vector. Do you see the elimination of variables that we're working so hard for? One, we're relating currents to voltage drops, and then we're saying, oh yeah, by the way, instead of relating currents to voltage drops, let's relate currents directly to node potentials. For our specific example, this equation ends up looking in this form. These are the scalar values. And we say that the currents across the resistors are going to be given by this matrix multiplied by the non-ground node potentials. We're now ready to move on to step 8c, which is to state the grounded KCLs. Remember that Kirchhoff's current law states that the sum of all currents coming into and out of a single node go to 0. We saw in step 5c that meant that the entire incidence matrix transpose multiplied by the vector of currents running through each element sums to 0. But in this incidence matrix, the columns are indexed by the nodes. When we take the transpose, that means that the rows are indexed by the nodes. And what we're saying is, when we ground this matrix, we want to delete all reference to the ground node. So we can actually delete the dth row from this equation and get the grounded KCLs. This is where we recall back to our fluency with matrix algebra. Remember, if we have a matrix-matrix product and we take the transpose, A times a matrix D, transpose, that transpose actually gets distributed to each matrix, but in the reverse. So A times D quantity transpose is D transpose times A transpose. What that means, though, is if I want to delete the row of our entire incidence matrix corresponding to the ground node, I could multiply on the left. Left multiplication manipulates rows by the grounding matrix transpose. But when I multiply on the left by the grounding matrix transpose, I could swap them and take the transpose out. This matrix on the inside is the grounded incidence matrix, and thus, when we're stating the grounded KCLs, deleting the proper row of this thing, I actually get a version of that exact grounded incidence matrix that I've seen in my previous steps. In other words, to go from the entire set of KCLs that has explicit reference to the ground node to the grounded set that deletes that reference, we multiply the entire equation on the left by our grounding matrix. That deletes the row of the left-hand side and the row of the right-hand side corresponding to ground node. And then that leaves us with our grounded KCLs. But remember, this matrix is actually block partitioned. And when I take the transpose goes into the block partitions. Please, viewers at home, check the dimensions for yourself. I've kind of written some of that here. But when I look at the grounded KCL equation, that means I can write it in subblock form. And specifically, we can almost imagine this as like a vector-vector product. That's one of the really nice things about subblock multiplication. So in particular, imagine this was a row vector and that's a column vector. I would just take entry 1, multiply by entry 1, entry 2, multiply by entry 2, entry 3, multiply by entry 3. Of course, the way that we block partition our columns here has to identically match the way that we block partition our columns there. But that works out based on the way that we structured our matrices. So we can turn our grounded KCL into a summation form where AR naught transpose times IR plus AV naught transpose times IV plus AI naught transpose times II is equal to 0. Remember that I sub I are known constants. The entries of that vector are the individual current source values defined in my circuit schematic. Just for good form, let's go ahead and take a look for the specific example we're looking at. The KCL at node 1 is going to be given by the first row of this matrix multiplied by my current vector, and that's going to be equal to 0. KCL at node 2 is the second row, etc., etc. Notice that the columns of my grounded incidence matrix transpose are blocked partitioned, which means that I can break this into the appropriate blocks. That's exactly what we've done here. Here's the resistor subblock. So I just pulled off those first 8 columns or M sub R columns. Here's the voltage source subblock. Here's the current source subblock. In this case, the number of zeros is equal to the number of non-ground nodes in the circuit, since each row of the transpose corresponds to a specific node in our circuit. This is where we do some pretty creative work. Because these are known constants, we can actually bring the known values over to the other side, just make that negative and bring it there. And that's known in other places in mathematics as a forcing term. So specifically, we could state the grounded KCLs with a non-zero right-hand side forcing term that encapsulates the effect of the current source on each node. So where are the current source touching the specific non-ground nodes in the circuit? That's what's been happening here. And this is really powerful because now we have a known right-hand side. This vector I sub r from step 8b in this video, we've seen that we can write that in a different way. Specifically, we could say that I sub r is G times A sub r times U naught. But check that out. That means if we combine those together, we get this system, AR naught transpose times G times AR naught times U naught plus A sub V transpose times I sub V equals negative A sub I naught transpose times I sub I. Right-hand side is known. This is almost a linear systems problem, except that on the left-hand side, we actually have 2 separate unknown vectors. We have the vector of node potentials, non-ground node potentials, and then we have the vector of currents running through the voltage sources. Now, formally speaking, we haven't studied this structure in linear algebra, and in fact, this equation gave headaches to electrical engineers for many decades. In 1975, there was a group of electrical engineers that discovered that you could actually state this equation in a larger matrix structure and used non-singular linear systems problems to do so. And so remember that we said that the voltage drops across the voltage sources was the voltage source subblock of the grounded incidence matrix multiplied by U naught. But here's a claim. If you combine the first block equation with the second block equation, you can state what I will call the modified nodal analysis system. The reason I call this modified nodal analysis system is there's a famous 1975 paper that actually introduced this as a generalization. Now, in the work that we're doing, we're not going to discuss including dependent sources, so sources that are controlled by current or voltage. The modified nodal analysis algorithm actually does include that, but what I want to state is when we have these systems, we can actually write that in the exact form that modified nodal analysis espoused. And if you check this out, this first row multiplied by that unknown column, the node potentials for the non-ground nodes, and then the currents running through the voltage source, that's that equation. Go ahead and check the dimensions. I've written them there for you so that you can do that quickly. The second block equation, so AV naught times U naught plus 0 times I sub V is indeed equal to that right-hand side. I'm going to claim that this is a non-singular linear system problem with large dimension. And if we solve that, we would actually get all the node potentials that we want. Now, to be very explicit for our specific example, this matrix actually takes the form that you see here, the 1, 2, 3, 4, 5, 6 non-ground nodes. That matrix right here, G1 plus G2 is in entry 1, 1. In entry 1, 2 is negative G2. Entry 2, 1 is negative G2. That 6 by 6 matrix is the one that you see here, which makes sense because it should be the number of non-ground nodes times the number of non-ground nodes. Down here is going to be the voltage source subblock of the grounded incidence matrix and a copy of the transpose there. On the last part of the matrix, we're going to have a matrix of all zeros. In this case, it's the number of voltage sources cross the number of voltage sources. That's a 2 by 2 matrix of all zeros. Here are the unknown values that we want. And then the right-hand side, these are the contributions of the current sources to the individual nodes, so node 1, node 2, node 3, node 4, node 5, and node 6. Let me say that in a different way. If you look right here, we see that in node 2, current source 1 is going to be going into node 2. That's why it has a negative. In node 4, current source 1 is going to be going out of node 4. That's why it has a positive. Node 5, current source 2 is going to be going into node 5. Node 7 doesn't show up because it's ground node. The last two entries of this are the voltage source values. That's the classic general linear systems problem that we've talked a lot about. Some of you might be wondering, how do you get these individual entries? The way that I think about this is the diagonals. Remember that the columns and the rows in this situation are going to be the nodes. And that's because the rows of A sub R transpose are the nodes that are connected to resistors. The columns of A sub R naught are the nodes that are connected to resistors. So nodes, edges, nodes. So here, when you're looking at node 1, notice that node 1 has both resistors 1 and 2 connected. So the conductances are G1 plus G2. When I'm looking at the intersection between nodes 1 and node 2, notice that between 1 and 2, I have only resistor R2, and I have a negative there. We can talk more about that in a different video, but the fact is, for node 1, it's mapping all of the resistors that are incident to that node. When I'm looking at node 1 and node 2, it's mapping all of the resistors that show up between that. In this case, it's only G2. Similarly, I could look in node 2 and node 2. Check this out. What resistors are incident to node 2? Well, it must be 3, 4, and 2. G2 plus G3 plus G4. What's the interaction between node 2 and node 1? Well, it's resistor 2. What's the interaction between node 2 and node 3? Well, that must be resistor 4. There are no other resistors connected to node 2. That means no other resistors will show up in either that row or that column. When I'm looking at this one, node 3 has resistors 4, 5, and 7. 4, 5, and 7. And then in between node 3 and node 2, I see resistor 4 shows up. In between node 3 and node 4, I see resistor 7 shows up. That matrix actually encodes how many resistors are incident on each node, and then what are the interactions between nodes in terms of the resistors in the circuit. And on the bottom, of course, we get back to that general linear systems problem. We're now officially done with step 8. We've stated the modified nodal analysis equation, and we've also stated the grounded analogs to the circuit equations. I do want to mention this specifically, though. Up through 1975, this was seen as the state of the art, and the modified nodal analysis algorithm is still used today in practice in CAD algorithms. But what I want to say is, I have heard engineers say that it's actually not possible to get rid of this term in the matrix equation because it just is voltage source information. But I'm going to claim the main insight that I had when I was working on this was this vector has interdependencies that relate to this matrix, and we can actually define vectors that annihilate this term and turn this thing into a very, very classic structure in linear algebra, which is A transpose CA times some matrix is equal to a non-zero right-hand side vector. Under a certain assumption, that thing will be positive definite, and that's exactly what we're setting ourselves up to do in step 6 of this algorithm, as well as steps 9, 10, and 11. So the claim is, even though we have a non-singular linear system, we're going to use some more linear algebraic theory to eliminate redundancies in this equation and turn it into a very classic structure in the exact form that we would like. Let's go on to step 9 and see how we start that process. I'll see you in the next video.